Start the recording. Okay. So first, I want to clear up. I want to clear up this confusion, miscommunication, which makes everything all very complicated. The lab sessions are live, which means if it is those who are in GH section, you have to be live after our class, starting at 6:50, going on to, I forgot now, 8:30, something like that. The TA assigned for GH is Legendre, Gabrielle Legendre, and she is live. She will be in Marshak. In room Marshak, room 407 North. And now, the labs don't start. Actually, the labs don't start till September 1st, which is Wednesday. And then next week is a holiday. So GH lab recitation section, even though you meet later at 6:50, it's not the lab itself, and it's more just introduction. All right, the actual lab, I think, starts September 13. The TA will be sending you the communication, and I've asked the TA to send a CC to me so I know roughly what is the communication. All right, now there is the issue. If you are section GH, you are now online, and you're supposed to be at Marshak room 407 North at 6:50. You cannot be at home and then expect to be in Marshak within 10 minutes. You probably need to be, not probably, you will need to be on campus. And now I asked, where is the study space before the lab opens? Because the lab will open Marshak room 407 North at 6:50. And all I know, according to the website, according to whatever is the official communication, is that no study space designated yet in live means you have to be in person. All right, if you need to ask, you ask aloud, because I cannot read that well so far away from the terminal monitor. So now, when you are on campus, so far they have designated some study space in NAC building, some rooms, I don't remember, 4th floor, 5th floor, so on, and some rooms in Shepherd Hall, again, some numbers, and then in the library, but you need reservation. So it is not a good situation. If I were the one that's involved, oh yeah, thank you. Somebody has all the things up there already. So you already know where you're supposed to go. All right. Now, I am sort of helping make the situation less of a intense by saying it is your lab grade that matters, not your attendance at all recitation sections. In other words, the TA is not going to say, somebody never showed up in my recitation section, therefore 0 for the lab grade. I say no, because it may be that you know a lot from the lectures that you don't need recitation section, because in a way recitation section is almost like a tutorial, because the TA is ready to help. You say you don't quite understand this decibel, you don't quite understand the superposition of standing wave. He or she, in this case, will be there to help you. So recitation sections are not mandatory as far as I'm concerned for the lab grade. You understand what I'm saying? The department may yell at me, but when they yell at me and say, no, 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 then I will announce that the department says, no, 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 no. But my own personal feeling is your lab grade is dependent on your lab report. You must be present for the lab. You must do the lab that they say you have this to pour down here, that to add down here. You must be there in person to do it. All right, is this now more clear to you?
Hi, Professor. My name is Stanley, and I have a question for you.
Yeah.
So I have lab tomorrow at 2 p.m. My
Right, yes.
my lab section is GH2. Now,
Yes.
is this in person tomorrow in room 407 North?
Yes. All these in-person lab recitation sessions are in this MR Marshak 407 North. At the time that they say 2 p.m. In other words, whoever's the lab supervisor, because he is in charge of the lab, he will open the door for that time period. All right? Is that
Yeah, but you said
enough?
that in-person lab starts after the first. So
right. So therefore, tomorrow you won't have the lab. You will have recitation. You have introduction rather, because the TA will say, you know, you better be sure that you bring this. You better be sure to bring, you know, whatever it is, and that they have. So the lab supervisor told me, generally this first introductory session may be only 30 minutes or less. All right, and maybe the TA will be ready and willing to say, anybody has any questions on recitation that need you know, help. So it is in that way very informal, the first session. But the actual lab starts, what is it now? I get confused myself. September, because the following week is a holiday, so I think September 13th, something like that. The lab TA will tell you when does the actual lab number one, when does it start? And it may be that for GH2, they start, because you meet tomorrow, September 1st, and so it may be September 14th, something like that. All right.
I understand. Okay. So tomorrow show up for recitation, and the actual lab begins for me on the 14th. Got it. Thank you.
Something like that. I mean, I get confused with the dates because of all the holidays here and holidays there. You know, later on you have yes.
So lab is going to be every other week. It's going to be 1 week recitation, and then the next week is going to be lab, and then
that's right.
And it goes
that's right. There's sort of like a alternate weeks. You have lab, I don't know, let's say September 14th or September 13th. Then the following week, September 20th, is recitation, and then September 27th is lab number 2, and so on. Okay, they alternate. So that in the end, there are 7 labs that you have. Is this sort of clear? And for the actual, you know, dates, you better be watching out for the communication with the TA, because the TA, they are the one that, you know, have that. And I tried to go online to find out the actual dates for lab number 1, actual dates for lab number 2. I cannot find it because it's very confusing. It depends on whether you're GH or GH2 or GH3. So, all right. Any other questions? Okay. If not, then we are clear, right? And as for the study space, well, maybe by after next week, the administration will have also pronounced some space in Marshak, for study space. Okay, so now let's come back to what we were on. We were on decibels, meaning a way of measuring the sound intensity that comes into our eardrum. Because after all, you need to hear. Last week, you couldn't see me, but you could hear me. This week, you can see me and you can hear me. Well, that's because I made sure that the video also works. Now, there is a way of measuring the sound intensity. And one thing that is very remarkable is that the ear measures the sound intensity not linearly. It's not like saying, ooh, the intensity is now, let's say, twice as intense. Oh, that now my eardrum can sort of react to it according to how much you impact my eardrum. And now you hit me with double the force. Whoa, and the eardrum will say, it hurts. And you will say, I don't like you. I send these sound waves that are 10 times. And then you say, ooh, that hurts 10 times. The ear does not measure according to how the waves, the sound waves, impact according to your intensity linearly. You understand what I'm trying to say? Linearly, right? Namely, if you were to be so angry and you now want to go chop on the table, right? Now, if you chop, you at first you're not so mad. You chop, you say, yeah, I can play with it. But if you really are so mad and you really want to chop very hard, the one that hurts is you, right? And later on we'll learn about, or maybe you already learned about it in your 203. So the thing about the sound wave, the eardrum, it measures it logarithmically. It measures it logarithmically. There is your intensity. And the threshold for a young one like you, your threshold that you can hear is 10 to the minus 12 watts per meter squared. My intensity threshold is now poor. There are times when my wife says something and I sort of didn't quite understand or didn't hear it, and then she says, didn't I already tell you? It's because, my eardrum, my ear is full of wax, well, I don't know, it's different people have different, so they begin to cloud up so that I'm not as sensitive. But anyway, the decibel is a way of measuring what is the intensity as measured with respect to this threshold on the logarithmic scale. And this logarithmic scale is on to base 10. So if let's say that you are 100 times more intense because you are yelling at me, and because I couldn't hear, you yell at me, and the intensity now is 100 times. If the intensity is 100 times, log to base 10 is only 2, because it's 10 to the power of 2. And then the decibel is now, you say it is 20 decibels. That the sound intensity that I now hear because you're yelling at me, that the decibel difference is 20 decibels. All right? Even though you actually were 100 times louder in terms of the sound wave, but my decibel, as far as my ear will only measure and recognize that it is 20 decibels. And there is this table here. The table gives you this measure of what is the decibel. First, if it is threshold of hearing, it is 0. It is 0 for you. It is certainly 0 for me, because my threshold is not like yours, it's higher. And when you say that the intensity decibel that I hear is a whisper, you notice it says a whisper, that the decibel is 20. What that means is that your sound wave is actually 100 times the sound wave of this threshold. So you actually are now sending the sound wave, and it is 100 times, but the ear only measures it logarithmically. So it only says, hey, it is 2, because log of 100 is 2, then it is 20 decibels. But now if you now say normal conversation at 1 meter away, the decibel is 65. And for some of your old folks, for your parents and grandparents, they probably can hear only if you are talking loud. Normal conversation, you may not be talking loud. So for them, it's not 65 decibel. They may only hear it at 1 decibel. All right. So when you are now trying to figure out what is the intensity, the actual intensity on your ear, that can be 10 to the 6 times. If it's 10 to the 6 times, it is 60 decibel louder. All right. And the threshold of pain is when you are talking about you're standing in front of a jet engine. When you're standing in front of a jet engine and you don't have a muffler, then what happens is the sound wave from the jet yelling and screaming at you is reaching you at 10 to the 13. 10 to the 13. That means it's a billion. 10 to the 6 is a million. 10 to the 9 is billion. 10 to the 12 is a million billion times. I mean, it's really loud, and that's where your threshold of pain comes in. Okay. And so now they have an example. They say, hey, I have a amplifier that is rated at 20 watts, and I want to compare it with a amplifier that is rated at 200 watts. And this 20 watts system 1 produces 90 decibel because the speaker, it is able to vibrate, and it's able to send out these sound waves, and the intensity has been measured such that it is 90 decibel. Meanwhile, this 200 watt, it sends out the music, sends out the sound wave at 93 decibel. You know, those sound engineers, they have these instruments to measure. Okay. Now, they just want to know, what is the actual difference in intensity? One is 90 decibel, one is 93 decibel, and then they just work. This is algebra. And they say, well, from the first guy, it is I1 over I0. From the second guy, it is I2 over I0, where I1 refers to the intensity coming from this speaker, and I2 represents the intensity from this speaker. And now you want to know what's the difference. I have 90 decibel and I have 93 decibel. What now is the difference of the actual intensity of the wave that is banging on my eardrum? And now you do the math here. You say beta 2 is this logarithm, beta 1 is this logarithm, and you know in algebra definition of logarithm, logarithm minus logarithm is the same as logarithm of the ratio. And if you have the ratio, this then becomes the ratio of I2 over I1 because I0 cancels out. Therefore, this now says you actually heard 3 decibel difference. Those sound engineers, they actually were able to measure, and they say, your 20 watt, for which you paid, I don't know, let's say $50, $100, and it's giving out 90 decibel. Whereas the second one, oh, you paid a little bit more money. I don't know how much more money for a 200 watt, but they charge you more money, right? And it is 93 decibel. So the difference is 3 decibel. And now you can say, but what is the actual intensity that impacts my eardrum? Well, this then algebra says 0.3 is logarithm to base 10 of I2 over I1. Therefore, I2 over I1 is 10 to the power of 0.3, which is 2. That means that the intensity of the wave sound that comes from this speaker is double. And the intensity is double, it's only 3 decibel. All right, this is just to kind of get familiar with this way of measuring the sound intensity that comes to your ear. Am I going too fast? Okay, no questions, right? Okay, all right. Yeah, there's no Discord, is there? Yeah, there's no Discord. Okay, let's go on. Yeah. All right, so now this is sort of that thing that gives us the difference in the sound intensity. And I downloaded this picture of the eardrum. And as far as I know, I don't know biomedical people, whether there's anyone who is able to give you a new eardrum because something happened to your eardrum. You know, never, never, never poke anything so sharp as to break the eardrum. If you were to break the eardrum, I don't know, is there any medical procedure that can now replace your ear? Have you ever heard of it? I don't think so. Oh, you have? Gee, I don't think so. There is repair, yes, but not rebuilding your entire ear. You know, like they cut open your ear and now put in a new. I transplant the ear from your friend. Your friend is named, lend me your ear, and then the friend says, oh, really? Here, I will cut out my ear and lend you the ear. Does that ever happen? I hope not. Right? Anyway, so this shows you the complexity somehow that this cochlear eardrum measurement, unlike other measurements, gives you logarithmic scale. Unlike when I want to chop the table and I get so mad, man, that measurement of pain is linear, but this measurement is totally logarithmic. And now, I had not included in the syllabus the standing wave or linear superposition, but since you will have a lab on standing wave, I have taken chapter 17 because my syllabus, I sort of based it on my previous professor who taught it 204. So he somehow did not have standing wave, so I didn't. But now I have imported from chapter 17 just the section on linear superposition. So here we want to now say, hey, what if I have now, let's say, 2 waves that are merging, right? On one side, you have a wave that is coming from the left, and then you have another wave coming from the right. Now, when they merge, what happens? That's what you call superposition. If one side is coming like this, They cancel out. Thank you. You see it yourself, right? If you have one side coming like this and the other side coming this way, and they are the same frequency, you know, they were coming with the same velocity, the speed of sound, and then they have the same wavelength, then if they are now superposed exactly one on top of the other, because when they actually come merge together, it's one above the other, they cancel. So when they are actually here, when they merge, there's no sound. But afterwards, oh, this side goes on and that one goes on, and you have this wave going that way, bye-bye, and this wave going here over also say ciao. But the moment they actually met, they canceled each other. This is what you call principle of linear superposition. All right? That's the language. And now we have, well, this is again just, if there are two or more waves, it's the same thing. You just simply add them. And the important thing is, what is their phase? P-H-A-S-E. What's their phase? Are they in sync or are they out of sync? This one is in sync, because when they meet, both are up. So this is now higher. The amplitude is higher. Therefore, the intensity is higher. This is what they call constructive interference. But in this case here, where this guy is high, this guy is low, you meet. I guess you don't even say hello. You say, what happened? I didn't hear anything. All right? So this is destructive interference. Okay? Now, so this is the basic idea behind what you call superposition, the linear superposition. And so now when two waves meet, you have a speaker, a receiver that actually has two speakers. You know, I don't know about your monitor. Some of these monitors now have stereoscopic, that they actually have two speakers in your monitor. Have you had that kind of monitors, laptops that have two speakers? Yeah, of course you pay more money, right? Yeah, you pay more money because there's more technology involved, and of course technology costs money. Well, what happens is your laptop, your whatever receiver sends the sound to this speaker and sends the sound to this speaker, and this speaker will now send out sound waves. C, I guess, stands for condensation, compression, and then R stands for relaxation, right? So you have compression, relaxation, compression, relaxation, compression, and this sound wave comes from this side, that sound wave comes from that side. Now, if you have it in phase, meaning when the sound wave comes out from this left speaker is exactly the same instant as the sound wave that comes from here, meaning it is high, it is compressing. Let's say here, compressing. And when it came out, this is the compressed wavefront, this is the compressing wavefront. When they arrive in the middle, they are adding, they are constructive. You see? And so what you now hear when you are down here, what you now hear is louder. Right? I mean, that's And if you now have difference out of phase, namely where this one was sending out, this side is relaxing. And if that is the case, from A, I guess they call this, no, from whichever side, you have this left side, this is the wave, right side, this is the wave, such that when the left wave is at a high, the right wave is at a low. If that happens to be the way the sound wave came from your speaker, from your receiver, from the two left-right speaker, then you are in the middle, you will find, whoops, they cancel, I hear nothing. And now, for us, in terms of, let's say, daily life experience, the reason why you want to have a stereo is that you want to have the speaker on the left produce a sound that you would ordinarily hear with your left ear. Am I shaking the left ear? I'm shaking off my wax inside it also, right? Here's my left ear. And the right speaker is now impacting on my right ear. And whatever comes out on here is what you, a live person, would hear with the left side. And whatever comes out from this speaker is whatever the right side will hear. That's why I get stereoscopic. I will then be able to say, yeah, I can tell that in fact the singer is now more or less on the left side of the room, and is the choir, the people on the left side is now singing sweetly, whereas the right side, they are just humming along, they are not singing. And then I hear the right side now coming in, with just the right time, so that this whole song is so sweet, right? Now, well, this we've already seen, so we don't need. And now we come to another practical application. The practical application which people do buy. You pay for it. You buy one of these things. What do they call it now? Muffler? Is that what they call it? A muffler? A sound, canceller or whatever. I don't have it because I don't. But there are people who, when they go on a plane or train or whatever, they get this so that there is no noise to them. What do you call it now? Yeah, there's a name for it, headphones, but there is a name that cancels out the noise. Not all headphones.
Sorry, Professor. I was going to say, I think it's literally just noise canceling headphones.
Yeah, that's right. There are, and you pay for it. Not all headphones cancel the noise, the noise around you. And what they do is they have a certain circuit down here, right? And then what they say is, what you hear on the left, the signal, then what you hear on the right, they shift it. Earmuffs, I don't know, there's a name for it. Maybe it's called earmuffs. It's to cancel the noise. And what they do is they shift the signal that comes through the left versus the right out of phase. So whatever is your signal, and it is right? And on the other end of it, they will now make a delay. That's what electric circuitry is. They put a certain delay so that what comes out is when this one is up, this one is down. So then when you hear it together, they cancel each other. Earmuffs keep your ears warm. They don't cancel out the noise. But anyway, of course, they do cancel out the noise in the sense that you don't hear, your family yelling at you and say, it's dinner time. How come you don't come? But I have my earmuff on. But this is the noise canceller, right? Now, you leave it to those sound engineers who know how to do the things so that they take this input and then they flip it around by delaying it and flipping it so that the net sum is 0. They cancel out. And so this is what the scientists will now say, that the sources are coherent for two ways. But yeah, okay, anyway. So this is when these are coherent, namely they are in sync, either totally in sync or totally out of sync, but they are in a way coordinated. Coherent is, am I being coherent or incoherent? Oh, people don't know the difference. Huh?
Coherent.
Yeah, hopefully I'm being coherent, right? If I'm incoherent, I would just simply say, what am I talking about? I don't know what I'm talking about. Yeah. But coherent means that these sound sources, they were coordinated however they came. And now if this is in phase and you are in the middle, or you hear it very loud. If they are out of phase and you're in the middle, you say, I hear nothing. So they have an example, and it's an easy, simple example. You have two speakers. They are 3.2 meters apart, and you are 2.4 meters away from this speaker, right? And now the question they want to ask is, what is the sound that you hear down here, assuming that they are coherent? Incoherent means there's noise from here, noise from there, and then all you get is noise, noise, noise. But coherent is when the sound emitted from here, it is the same phase, P-H-A-S-E, as this side, but you are closer to this than to that. All right? And so they want to now know, can we now figure out what is the sound that you hear? Well, you do the math here. You say, okay, I know this is 3.2 meters away. I am 2.4 meters away. Therefore, I am 1.6 meters longer than 2.4. Are you following this? Because the hypotenuse is here. And then you want to know minus this because you are trying to see what is the interference. So the path length, the length of this, difference between this length and this length is 1.6 meters. And now the wavelength, the wavelength now is the velocity of sound divided by the frequency, and you are told that the frequency is 214 hertz. Therefore, the wavelength of the sound that you hear is 1.6 meters. And because the difference is also 1.6 meters, you get constructive interference. Are you following the reasoning here? Yeah. Let me say it again because you may not realize. We are told that the sound is, I don't know, 214 hertz. Whether it is yelling 214 hertz, I'm not a musician. I have no idea whether this is a high C, low C, and so on. But anyway, the frequency they told us is 214 hertz. And now the velocity of sound is 300, about 30 meters per second. Therefore, the wavelength of the sound that comes from this and from this is 1.6 meters. But now you figured out, not told us, but you just figured out that the difference between this and this speaker, that this wave traveled 2.4 meters, this wave traveled 1.6 meters more than 2.4. So it's 4 meters. It traveled 4 meters. And therefore the difference in the wave that it traveled is 1.6 meters, but that's exactly what is the wavelength of sound. So you are still in phase, you're still in sync. So therefore you will hear loud. It's constructive. All right. So, and there are these, again, examples of these engineers who are able to make it such that it is destructive. They are able to make it out of phase so that it is destructive instead of being constructive. And now I will finish with a slide because it is an important application in our real life. Of course, you want to buy those speakers that have all those nice gadgets, sure, but when you are in a concert, there are the people who design an auditorium for a music auditorium for a concert, whether it's an opera house, whether it's a rock concert, they install these clouds. You know, these are the panels, right? Now, these panels, you know what they do? They try to help all the people who have already paid for a opera. I don't know how much it is these days, whether it is what, $50 or even $100. You know, if you want to be right near the stage, whatever, you have paid money to be in this auditorium. And now the soprano who is on stage, the soprano, oh, she or he, no, soprano is what? Soprano, is it male or female? Can you be a soprano if you are female? Okay, all right. So what is male? If I am a good, am I also a soprano? If I am a famous singer, am I also a soprano? I don't know. I'm not a musical guy. If your voice is high enough, but anyway, the point the point is that here I am, not yelling, but I'm singing at the top of my voice, right? But now at the top of my voice, there is a voice that comes to you, right? From the soprano. And I am sitting, let's say, on the third row or fourth row. I hear you directly. But I also hear the reflected sound, right? I also hear the reflected sound. And now what you want is that when you're sitting here, that you actually get constructive interference, not destructive interference. You following me? You want it such that you hear the sound that was from the soprano, and it is, you know, at whatever is the so many hertz frequency. And now there will also be sound wave that went up and now reflected down here. And sound engineers, those sound for which they charge a lot, right? They now will have the cloud, these reflectors, at the correct angle so that you sit here, you feel the full, you know, you hear the full, the whatever aria that they are singing, all right? And if you have a concert and you have a orchestra down here, and there are people with violin, oh, then you also want it such that the violin, they're already synchronized, that the sound wave from this violin coming here, oh, is not cancelled down here, but that it is now constructively interference. And the reason why these people who design these music auditoriums, they need to hire these sound engineers, is precisely to enhance your experience, right? So just be aware, let those sound engineers, they they designed it. And for such famous like Carnegie Hall, or there's a famous hall in Italy somewhere where they are very famous. There, they in the early days they did not have these acoustic reflectors. You know what they have? They have curtains around. Have you seen those? Carnegie Hall, or the famous hall in Vienna, in somewhere in Italy. What they have are these curtains around, and the curtains act as reflectors. You may not believe it, but it has to do. That's how some of these people will say, this is a Carnegie Hall experience that you now in this modern looking auditorium try to reproduce. Okay, so anyway, you are biomedical, I'm just a theoretical physicist. I'm not, but just be aware that people do pay a lot of money to help enhance your musical experience. Okay, any questions? Is anybody going to now sing an aria for us? What was the question now? I didn't get to read it all. Somebody had a question. No, I can't hear you. So
it's saying that
yeah.
the exam questions are going to be more conceptual based or mathematical, like problems and stuff like that.
Right. There will be a mixture. There will be some questions that are conceptual, so that you sit and think, because it helps you to understand the concept. And there will be some which is just putting in the numbers. Putting in the numbers is not really such big a deal. What's more important is you as biomedical profession, you want to know more of the concepts so that you can appreciate, and then you'll be able to make use of whatever instrumentation that you have for later on. We'll see ultrasound. And then you will not be able to say, well, ultrasound, oh, I understand the actual technical principles deep inside ultrasound, but you know the application of ultrasound. So you appreciate the concepts that are involved. Okay, so there will be conceptual questions, and then some simple sort of like applications of simple formulas that I will emphasize and say, this is the formula that you use. Okay. All right. So now let's go on. And now we come to something which is more complicated, but actually it's in our daily life. Have you ever been in your train station or subway station and the train is coming? Do you hear them have a sound, right? And can you tell the difference between the sound of a train that is coming to you and the train that is going away from you? Have you ever heard it? You must have, right? Yeah. And if you live near a railroad track, and even in the middle of the night, these trains, they are filled with whatever is the freight trains. When they come, they will always have, the horns, right? I don't know how to reproduce the sound of a passing train, but it will be whatever, and then you can tell when it is coming towards you, the frequency goes up. Then after it passes by, the frequency goes down, right? You have heard that, and you have seen that passing train. Well, Now we want to make use of that and say, let me understand the concept of something called Doppler shift or Doppler effect. I forgot to check who is Doppler. I guess you can look up to Google yourself. Somebody from long time ago. Yeah, you love the Doppler effect. You know, it's very fun, you know, to sort of appreciate, and then you can even close your eyes and then you say, "Woo, I know a train is passing by and it went away that way," right? It's a uplifting experience, especially when you go for a walk in the whatever morning or so on. Okay, here we now want to study this Doppler effect, and the book has the picture of first a train that is at rest. If a train that's at rest, oh, it will just keep emitting these sound waves, right? And these are now the sound waves, or we call it the wave fronts, right? And this is now the first wave that came out has traveled here. The second wave traveled here. The third wave traveled here. The fourth wave traveled here. And the fifth wave hasn't yet come out yet. So they draw this picture of, and then you are the observer, and you are at rest, and the source is also at rest. And you can now say, somebody said something about, oh, Christian, somebody, Andrew Doppler, is he a British or is it American scientist? No, somebody can find out. Or is he a European, you know, French, or if it's French, it will be Doppler effect, or if it is German, it will be Doppler effect, or whatever. Anyway, so Austrian, oh, then it will be Doppler. Yeah, jawohl, yes, jawohl, Doppler. The Doppler effect, you now say, hey, I am standing here, I'm not moving, and the wavefront passes me by. I know the wavelength, I know the speed of sound in air, therefore I know how long it took to pass me by, and I can figure out the frequency, right? We can write down the frequency. You remember the formula? Okay. Oh, I have to now again do this. Now, what did I press? Well, what did I touch that made it not work? Huh? Well, okay. I give up. I had it such that I could do it, but now I cannot do it. Well, all right. You know, it is V equal to lambda F, and therefore F frequency is V over lambda. Okay, so I can now say, yeah, I know the frequency. Because I know the wavelength, therefore I know the frequency, and the frequency is V over lambda. Okay, so I know this, but now I want to compare. The fire truck is at rest, I'm standing here, but now the fire truck started moving. The fire truck started moving, and so therefore it will emit a wave front, then it will emit another one, but at first the wave front that it emitted was over here, but now the second one is now going to come closer to me. third one closer to me, fourth one closer to me. Do you see this picture? Because the fire truck, oh, it is emitting. It continues to emit according to the, it has its own, what you call, the frequency. It's still emitting according to its own frequency, so many hertz. But the sound waves now, the wavefront now are being squeezed. Do you see how the wavelength that I now measure, because I am now over here, I measure and the wavelength is shorter. Is this clear to everybody? I mean, this picture kind of explains it, right? Self-explanatory. Okay. Because before, oh, this was the wave that was first emitted, let's say 10 seconds ago, and then this one is, let's say, 6 seconds ago, and 3 seconds ago, and so on. So they were all concentric circles around the center. But now this was the wavefront that was emitted while it was over here. But now this is the new wavefront while it is already moving. This is the new wavefront when, and this is the new wavefront when it is here. And it's since coming near to me, the wavefronts are actually squeezed closer and closer, right? All right, so now let us now do the math, simple math. At first, the wavelength is lambda, because you know I actually kept a the frequency and I know the velocity, so I know the wavelength. Wavelength is V over F. But now the wavelength is shorter now because this fire truck, oh, it is giving off these sound waves. So the first one was arrived, but the second one now is sooner because why? He's closer to me. And if I now say, what is the new wavelength? It's less. How much less? It is less by what is the velocity of the source times the period. Are you okay with this basic? I wish I could use this thing. I don't know. Does this work now here? No, it still doesn't work, so I'm sorry. Just because I put it down on my desk in a certain way, it stopped working. You follow this? This is the velocity of the source, and the wavelength is the velocity times the period, because this truck is moving with a certain velocity, and in one period it has moved dt. Therefore, my wavelength is shorter. In one period, it has moved dt, where v is the velocity of the source. And in that one period, it has moved this much. Therefore, the wavelength now is shorter. And the frequency that the observer now measures, FO is the observer. The frequency that the observer measures is the velocity of sound over the new wavelength. Because he says that, no, the wavelength is shorter, therefore the frequency is higher. Herr Doppler already figured it out. I don't know how many years ago, 4 centuries ago, 5 centuries ago. So here you have the frequency that the observer now measures is the velocity of sound in air divided by the shorter wavelength. And the shorter wavelength is the original wavelength minus the speed of the truck, the source, times its period. But the period is 1 over f. The period is 1 over f of the source. Therefore, algebra gives you that the observed frequency that this observer now measures is that the frequency is now higher. The original frequency from the sound of the truck, it was supposed to be 400 hertz, But now this observer will say, wait a minute, it's not 400 hertz. It now maybe it's 460 hertz. It's higher. And how much higher? Algebra says it is 1 minus the velocity of the source relative to the velocity of sound. The faster you go, if this is not a truck but a jet fighter, and the faster you go, the more is this frequency. You notice? Because I have the speed of sound, and if my truck is moving with a velocity that is close to the speed of sound, then the frequency now is very high. This is what they call Mach speed, M-A-C-H. We will, I don't know whether in this chapter we want to go into supersonic, when you indeed are moving as fast as the speed of sound in air, then you create a sound wave which becomes a shock wave, which is what they call the Mach speed. And if you have a supersonic plane that is flying across New York City, and it is going at 2 times the speed of sound, there will be a shock wave that comes associated with that, and your Empire State and so on would all be saying, wait a minute, our windows are being shattered. So that's why FAA would not let any fighter jets pass over New York City at a speed that is greater than the speed of sound. Supersonic. When these supersonic planes come near New York City, they have to have the speed slower than the speed of sound in order not to cause a shock wave. All right, but anyway, the main thing of this Doppler effect is that the observer will say that the frequency is now higher by this ratio, 1/1 minus velocity of the source over the speed of sound. Are you okay with this? Okay. I'm sorry, I wanted to also write on it, but somehow these things always make strange difficulties. All right, but now we have already said that. When I was preparing for tonight's lecture, I already made sure to write down that this is the velocity of the source, this is the frequency of the observer, this is the frequency of the source itself, right? This is when it is moving towards the stationary observer. But if it's moving away, then it is the opposite. When it's moving away, you remember over here, if you were over here, if you're moving away, there is more of a separation. It is not smaller wavelength, it's longer wavelength. Why? Because in that same period, you have moved. So in the case of moving away, it now is 1 plus. The wavelength is now longer, not shorter. And when you work through the algebra, it gives you this 1 plus. That's why when it is coming at you, the frequency rises, but when it is going away from you, the frequency goes down. So you have this train coming by and it's going toot, whatever is the sound, the horn. It will be now rising, and then it goes by, right? So this in one slide gives you the summary of Doppler effect. Okay, so now they say, hey, you have a passing train. It's going at 44.7 meters per second. That's quite fast. That's quite fast. I forgot now. For 55 miles per hour. So this is going quite fast. A high speed, train. It's going at 44.7 meters per second. when the engineer sounds the 415 hertz warning horn, the speed of sound is 343 meters per second. And now they say, what are the frequencies approaching and leaving the crossing? Well, when it is approaching the frequency that you observe, this FO is you as the observer. What you measure is the original 415 hertz, but now it is higher. How much higher? It is 1 minus the velocity of your source, which is the strain, divided by the speed of sound in air. When it has passed you by, then it is lower, and it is 1 plus the velocity of the source divided by the speed of sound. So anyway, so it then shows when it's approaching, you get the number answer, which is 477 hertz. When it is leaving, it's 367 hertz. And even if you are not a musician, an ordinary person will say, yeah, I can tell that the frequency has gone high, and then when it passes by, the frequency drops low. All right? Any questions? No questions? Okay, good. So now let's go on. Yeah, okay. Now, so far, the previous case was, let me show that again. You as an observer, you did not move. You stood. You are the observer. You stood either in front or at the back. You know, the train passed by. So you did not move. Now, the Herr Professor Doppler, he also now says, hey, you got to be thorough, right? As a scientist, you got to now also consider, what if Herr somebody, yeah, Herr somebody, hey, you, Herr somebody, what if you yourself as an observer are moving? And first, you just say the source is stationary. All right. Supposing the source itself is stationary, but you are moving. Well, the source is just giving off, you know, according to the period, and you know, after 1 second here, another second later here. Let's say if the period is 1 second, that would be the hertz. If the period is you know, half a second, well, there's one wave here, and then 1 second later, 1.5 seconds later, 2 seconds, and 2.5 seconds, and so on. So these are the wave fronts that are passing up from this stationary source. But Herr, I mean, that's not Monsieur, but Mr. or Herr, Herr is the German word for Mr., right? So Herr so-and-so is now walking. You are the moving observer. And now what happens? Is the frequency now higher or lower? Without, you know, just intuitively. Intuitively, would you now say, when you yourself are moving towards the wavefronts, are you now having it higher or lower? Yeah, intuitively, it's so clear, it's higher, right? The frequency now would be higher. How much is it higher? Well, it depends on your velocity, because frequency is always your velocity divided by the wavelength. All right, so you say the observer's frequency now is whatever was the original source frequency, but now it should be plus v over lambda. But now, if I write this out algebraically, this is now the source fs, and this is now 1 plus v of the observer, because you are moving, over fs lambda. because then it is the original formula. But F lambda is what is the velocity of the speed of sound, because this is the sound wave. So you now have Fs, the source frequency, then is 1 plus your observer velocity over the velocity of sound. Because this is the sound wave that you are dealing with, and whatever is the sound wave, wavelength times frequency is the velocity of the sound. And so you now have this formula that says that the observer will say, oh, the frequency is now higher. Why? Because I am being impacted by the first wavefront, then the second wavefront, the third wavefront, because I am moving towards it. And the frequency now is higher, and this is the how much it is higher by. So if I am moving towards, we have that formula. The observed frequency now is the original source frequency times 1 plus your observer velocity over the speed of sound. If you are moving away, well, it is now, I am saying, if this is the source and I'm moving away, well, it takes time for these waves to catch up to me because I'm moving this direction. So the frequency now would be less because it takes time for the wave to catch up with me. And so if I'm moving away, the frequency now is less, and the observed frequency now is 1 minus observer velocity over the velocity of sound. I mean, this is sort of being thorough, where you now consider the Doppler effect for a moving observer. And now they say, hey, you can now take the combination, the general case, because after all, engineers, scientists have to have the general case. And the general case would be, oh, if you were in fact moving, then the frequency would be either increase or decrease depending on whether you are moving towards the source or away from the source. And this is now the source itself could be moving. And if the source itself is moving, and if it is moving towards you, or the frequency increase, you take the minus sign. But if it is moving away from you, it would be the plus sign downstairs. So this is the general formula. Now, you need not be concerned about being tested on this. You just need to know the direction of the Doppler effect, whether the frequency increases or decreases, depending on whether you are going towards the source or away from the source, or depending on whether the source is moving towards you or away from you. All right? Is that okay? Yeah. Okay. All right. So now, let us now look at the, let's say, the practical. Practical in the sense that you as biomedical profession, you say, what difference does it make to me? We are, laymen. We are just, I guess, ordinary people. How does Doppler effect help us in improving the quality of life? I mean, these are, of course, the fundamental formulas which Herr Professor Christian Andrew Doppler had already figured out, I don't know how many 100 years ago. But today, people actually use Doppler effect. And now let us just go over some of them, because you want to be able to say, yeah, I now appreciate what Herr Doppler was able to figure out for us. Have you seen this? I downloaded this. Do people worry about this? What is this a picture of? Yeah, tornado, right? Yeah. Well, you should give thanks that it didn't happen in New York. But there have been these fierce storms where indeed there are local tornadoes. Yeah. And now in Louisiana, they are actually having a terrible time with tornadoes. And the question is, can you sort of have instrumentations that give you a sense of approaching tornado so that you can give warning? You see what I'm talking about? You want to now make use of science, and you now want to say, can science help make our life more, let's say, I wouldn't say our life predictable, because you cannot predict your own life, but more, what would be the word for it? More reassuring, right? Okay, because you want to say, yes, I know a tornado warning is coming by, and I better now within the, because when there's a tornado warning, it is quick. It's not like, oh, the tornado will touch down in 3 hours time. When there's a tornado warning and you get a warning on your handphone, it basically says, it's coming within the next 10 minutes, 5 minutes, depending on where the tornado is. Well, this is what a tornado is. It is air swirling about. I don't know if you remember from your 203. Hot air rises because the ground is hot, right? Hot air rises, but as it rises, it doesn't rise what they call a clear air turbulence. The air kind of turns around. It has to do with the fact that the earth is rotating. When you have a bathtub and you now, empty the bathtub, you will see that the water doesn't just go down. It kind of like swirls around as it goes down. And it has to do with the earth's rotation. And if in the northern hemisphere, I forget now, it goes is it this way? And then if you're in the southern hemisphere, it goes the other way. All right. I mean, the experts will tell you. But anyway, so here is your air that is rising. And it is now, a tornado is one where it's rising very fast, where these are swirling around with the velocity, I don't know, quite fast. And what the experts, the weathermen, the NASA people, what they are able to use is to say, hey, there is now, they send sound wave to it. They send a sound wave to it. So here is the wave coming by, but now the air itself is being moved around. So there is a Doppler shift. There's a Doppler effect. So when there is a wave coming this way, as a result of the air, the wind, as a result of the air, there is now the reflected sound wave, because after all, basically what this next radar is doing is it's saying, it's sending out a signal. And when it sends out a signal, it now is bounced off. It's bounced off this circle of air. And so when it comes back, it is at a different frequency. And it knows, Professor Doppler is a formula for the Doppler shift. And so they can then say, oh, I know the direction, because I send it, it was coming towards me here, it's going away from me here. Therefore, the frequency shift, I know. And therefore, I will say, oh, I know which way is this tornado going. And I am able to now send a warning to people and say, hey, watch it. The tornado is only 3 miles away from you. I mean, leave it to the, you have to really say the engineers, oh man, they deserve a lot of, thumbs up that they were able to design this to help the people to have a better life, because you know. And now, it does not mean that as a result of this, you are safe. It just means that be prepared. If there's a tornado coming, be prepared. And you also remember from your 203 that when there is a real tornado passing by, it can indeed lift up your roof because of the Bernoulli principle. You remember Monsignor Bernoulli, yeah? So it can indeed lift off your roof, but just be aware. There's this warning that says, hey, there's a tornado coming. Does not mean that if the tornado hits, you've been warned, you can now make your house totally be safe. That's not. It only tells you that there's a tornado coming. Just be aware and not be on the roof, not be anywhere, but sort of be safe in the basement somewhere. Now, there is another application of the sound, which is the ultrasound. Again, this is clearly even beyond me. I wouldn't know how to design it, but this took years of scientists, physicists, engineers to figure out a way of figuring out whether your baby is male or female, right? It used to be when a child is born, you don't know until the child is born that it's a boy or a girl, right? But nowadays, man, by 3 months, or is it 4 months or something, they are even able to say, hey, what you have is a baby. By the way, is this a baby boy or girl? You see the feet, you see the head, and you see the hand. Can you tell whether that's a baby boy or girl? I don't know. Are you the, huh? Can you tell? I don't know. But those ultrasound people, oh, they move the probe, here, she's having the probe, right? They move the probe around because the probe is sending sound waves. The probe is sending sound waves. Yeah. So when they when they do the thing, it is not just one picture. They actually move it around, and then they can now capture from different angles. And so they will have another one where they show, oh, I see that there is that this is a boy, right? So this is what ultrasound is, that they actually have these probes, and what the probe does is to send out the sound waves, and then it basically is probing inside, and they already know what would be, by doing many experiments, what would be the reflected sound intensity as well as the frequency due to your moving this here and there and there and there and there. And you then have a picture, what they have a whole three-dimensional picture of this ultrasound. And you as a practitioner, as a practitioner, you would then be able to record all of it and then be able to tell the patient, oh, that this is now a baby of such and such. And I'm very impressed that indeed today the ultrasound is so very let's say, good at probing, they can even tell the baby, your baby may have deformities. You know, and it's not an easy situation. But this one clearly is a normal one, because the baby is rubbing the eyes or something, and you have the hands and you have the foot. But if there is some deformity, ultrasound can also show you. So this is the real benefit of Doppler effect, because they are using Doppler effect, but they are using a very sophisticated analysis of Doppler effect from the way your body pulses versus the pulse that comes from this probe. Okay. Yeah. Okay. They say well, this is from the book. They say that this is the probe, and the probe, this is the skull. I didn't realize they can do ultrasound of the skull. Or do they mean the skin? Is this the skull? Do they do ultrasound of the head? You are the biomedical profession. Do they do ultrasound of the head? I don't think so, right? Yeah. So why do they say it's the skull? I don't think this is not right. This, huh? Yeah. So I don't think this is skull, or maybe they means the skin or something. It's not the skull, because my skull is oh, it's not an ultrasound. No, but they say ultrasound waves cause. Anyway, let this be a skin. They've opened the skull, and oh, they have opened the skull. Ah, they actually open my skull and then do ultrasound. Yeah, yeah. Well, I know that's medicine, medical, biomedical. Ooh, I guess if you have a tumor, then you do need that kind of procedure. That's very advanced. So they say it probes and it sends a certain, frequency. And by the way, the frequency here is 400 hertz. It's not 300 hertz. It's kilohertz. That's why they call it ultrasonic. Beyond the usual sound that our ear can hear. It's ultrasonic. Much more. The frequency is 23 kilohertz versus 30 hertz, 300 hertz, 400 hertz. It is 1,000 times ultrasound. And they shatter sections of the tumor that it touches. Yeah, I guess that's right. So this is the brain, and this is the tumor. And they can already see the size of the tumor. And oh, wow. This is, they can even tell it is a red blood cell. Ooh, I didn't realize that. When the sound is reflected from the red blood cells, its frequency is changed in a kind of Doppler effect because the cells are moving. These are the red blood cells, and because the cells are moving, there is the Doppler effect, the Doppler shift. The incident is at a certain frequency, let's say 23 kilohertz, and now this reflected one is, since this is moving away from the source, away from the observer, this frequency now, is it higher or lower? I am now asking my consultants here. The red blood cell is moving away, so is the frequency now higher or lower? Yeah, thank you. It is lower. Yeah, you see now how you have begun to grasp the concept. You have actually become more, expert. And knowing that it is the Doppler effect that people use, the engineers are then able to say, oh, the red blood cell, the velocity is blah, blah, blah. They are actually able to now say the velocity of the red blood cell in your vein is blah, blah, blah. And then they will say, ooh, normally the velocity should have been, I don't know, so many meters per second. But now your particular red blood cell is now going, what is it, slower. Supposing they measured and they say that your blood is flowing at a lower velocity than normal, what does that indicate about your blood, your vein, about your blood vessel? Do you remember the, huh? When your velocity is less, right? Because your velocity is less, then 1/2 rho v squared is smaller. Therefore, the pressure is higher. Of the pressure on the vein is higher. You got it? You remember from chapter, I forget what, 203. And so that itself is a warning, because it says that your blood vessel at this point now has a higher pressure, so that you can have, what is the name of the problem if you have, there's a medical term for it. If your blood vessel becomes blown up, what do you call it now? Something, there's a name for it. And then they say that's dangerous. Conversely, yeah, something, aneurysm. Thank you. Yeah, I remember aneurysm. Right. You're pretty good in the biomedical profession. Aneurysm. Okay. But now, if instead you measured and you find that the velocity is higher than normal, that your blood flow is now higher than normal, what does that tell you? You remember when you have a flow, if you now have plaque, when you have plaque, you narrow the amount of space for the blood flow. So then the velocity now is now higher. That means that you have a plaque, or you're likely to get a clot somewhere. So this is how these ultrasound has become so advanced that people are beginning to have these ways of figuring out, measuring from your blood flow what your medical situation is of your blood vessel. I mean, you got to now really say medicine has increased to such a degree that it is all coming from science, from general physics. Of course, more than general physics, it took decades of engineers working with general physics to develop all of these instrumentations. Oh, and then this is the sensitivity of the human ear. You have the intensity levels, and these are logarithmic scale. But anyway, I think, yeah. Any questions at this point? I mean, this is just for the real technical experts. They want to know what's the logarithmic scale and so on. But I think it is good to reflect on what science has been able to help to improve the level of medical care, of medical diagnosis, of medical procedures. Any questions? Yeah. Oh, and my battery is now just low, so I will plug it in. But anyway, we don't need to stay beyond. You can go. Yeah, for those who are in section GH, you have, what is it now? You have 14 minutes. Yeah, you have 14 minutes to be live in Marshak room 407 North. And I hope it is a good time that you have with Gabriel Legendre, that you introduce to each one another. By the way, you better prove that you have vaccinated. Okay, I will send the link, session link for Wednesday, and until then, have a good time. Yes, it's getting to be good night. So you lost your vaccine card. I don't know. You have to deal with the security guard. No, they'll have to handle it somehow. Yeah, I don't know. It's a very complicated situation these days. Okay, so let me. Yeah. Okay, so I will stop the recording.